Now that we've talked about rational functions, we've talked about polynomial functions, we're going to talk about just in general analyzing functions, particularly as it comes to limits. Because we're in pre-calculus, we are going to talk a little bit more about limits in preparation for calculus. So what is a limit? So a limit is the value of y that a function approaches as the input x approaches some value. Now, limits allow us to find or estimate the value of a function at a discontinuity or other value that is difficult or impossible to evaluate. So, in other words, if we know the behavior of the function, we should be able to talk about the value of the function as it gets closer and closer to some value x. Now, here's some stuff about limit notation. So this is typically how you'll see the notation. So on the left over here, the LIM here indicates that we're finding a limit. On the bottom, the X with the arrow to the A, that tells us what X value we are approaching. So the way we would read this first part is the limit as X approaches A. And then f of x is whichever function that you're using, whatever that function rule might be. You might just represent it with f of x. You might actually write out the function rule, whether it's a polynomial function, whether it's a rational function, or any other function. And then on the other side of the equal sign here, this y is the value that the function actually approaches. So the way you would read this is the limit of f of x as x approaches a is equal to y. Now let's talk about how you find limits. So the most basic case is if f of a exists, then the limit as x approaches a for f of x is equal to f of a. So for example, let's say here is the graph that you're looking at, and this function is f of x, and you're asked to find the limit of f of x as x approaches negative 5. So what this means is, what is the y value of this function as x gets very, very close to negative 5? In this case, well, it gets very, very close to 1. And in fact, it's equal to 1 because when x is equal to negative 5, our function is equal to 1. Now, this is very basic, and it's really basically the same as asking you what's the value of f of negative 5. So this isn't really the particular case where finding limits is really very useful. They're actually most useful when we're talking about places where the function is discontinuous. So if a function has what we call a removable discontinuity, or in other words, a hole, right? Removable discontinuity means you have a function, you have a graph, and you just take out that one point, that one discontinuity that you just removed. So if the function has a removable discontinuity, you will be able to find the limit. So a removable discontinuity is a value at which the limit of the function exists, but does not equal the value of the function at that point, possibly because the function does not actually exist at that point. So take a look at some examples here. So in this first one, we have this line, and we have a very clear hole at negative 2. So if you were asked what's f of negative 2 equal to, you would say, well, it doesn't exist. There's no value there because there's a hole. But if we wanted to use limits to actually be useful and give us more information, we could say, well, the limit of f of x as x approaches negative 2, so when it gets very, very close to negative 2, but doesn't actually reach negative 2, it looks like it gets very, very close to 4. And that gives you actually more information than just simply saying that it doesn't exist at that point. Now take a look at the second example here. We have a parabola that has a hole, and we also have a point as part of the graph. All right, so if you were asked what f of 2 is equal to, you would say, well, f of 2 is equal to what? It's equal to -5 because I have a point right there at -5. However, if you were asked what is the limit of f of x as x approaches 2, so if you look at the parabola, and as you get very, very close to 2, it looks like it approaches -2. So you can also see how not only does it does talking about limits give you information, like in example A here, but in B, it actually gives you more information. So although you did have information on what f of 2 is equal to, it wasn't quite the entire picture, right? The entire picture was, well, actually, as you get close to 2, it gets actually very close to -2. But at 2, it jumps to -5. Okay, so let's talk about calculating limits. Now we know that the limit would be equal to whatever y value would fill the hole in the function, as we saw in those last two examples. Now take a look at this function here, f of x equals x squared minus 2x minus 8 all over x squared minus 7x plus 12. So in this example, we were able to find an asymptote at x equals 3 and a hole at x equals 4. Now the asymptote is not removable, but the hole, on the other hand, is a removable discontinuity. Now, how do we remove it? So in other words, how do we know what the y value is? Well, since we know that the hole is at x equals 4, and how did we do that? We did that by factoring and then finding the zeros. So let's go ahead and start by factoring. So x squared minus 2x minus 8 factors to x plus 2x minus 4, and x squared minus 7x plus 12 factors to x minus 3x minus 4. So now we can see very clearly the whole came from that x minus 4 that's being canceled out. Now if you want to know actually where that hole is, you'll do exactly the same thing as what we were doing in our analysis with rational functions anytime you need to graph a hole. Right, you use the simplified version and you plug in 4. So now we plug in 4 and we have 4 plus 2 over 4 minus 3. So that's 6 over 1. So in this graph here, we know this is equal to 6. And so we can now say that the limit of the function as x approaches 4 is equal to 6. Now it is possible that limits don't exist, just like that iconic line from Mean Girls where Lindsay Lohan's character says, "The limit does not exist." So when does a limit not exist? This happens when the function does not approach a single numerical value. Now when don't you approach a single numerical value? There are two reasons where this might happen. The first is if you have a jump in the graph. And the second is when you have a non-removable discontinuity. So there are two types of discontinuity. Either you have a removable one, which is a hole, or a non-removable one, which is a vertical asymptote. So take a look at this first one here. We have a very clear jump in the graph, right? So as you move from left to right, once you get to x equals -1, it jumps up, and the rest of the graph is on the other side. So we would say the limit does not exist here. And the reason is because as you approach it from the left, it approaches -4. But if you approach it from the right, it's equal to +4. So we would say the limit as x approaches -1 for this function doesn't exist. Right, so it has to approach a single numerical value in order for that limit to exist. Now, for a non-removable discontinuity, so for a vertical asymptote, we also say that the limit does not exist. So here you can see that from one side it's approaching -infinity, and from the other side it's approaching infinity. And for that reason we would say that the limit as x approaches -4 does not exist. Now, if on either side of the vertical asymptote, you were approaching, they were both going up or both going down, we could still say that the limit does not exist because infinity or negative infinity is not a single numerical value. However, if it is the case, you are absolutely allowed to say that it goes to infinity. So at asymptotes, there are two acceptable answers for the limit if you have this case of togetherness at a vertical asymptote. So you can simply say does not exist, or you can say that it's infinity. So as x approaches -2, no matter which side you come from, it goes to infinity. Your y value is infinity. But it is definitely okay to just say that it does not exist because it is not a single numerical value. Infinity is not a single numerical value. Let's talk about limits at jumps. So for jumps, we said that the limit will not exist. However, it is possible to have what we call a one-sided limit when the graph approaches different values from different directions. And the way that we indicate which direction we're coming from in terms of the limit notation is we either put a plus, which means coming from the right, or a minus, meaning it's coming from the left, after the value in the limit. So for example, for this one that we just looked at, we would say the limit of the function as x approaches -1 does not exist. But we do have very clear values depending on which side we're coming from. So if we were to say, well, if I'm coming in from the right, I would say the limit as x approaches -1, put a little plus sign after it that indicates that it's coming from the right, and we would say that that limit as x approaches -1 from the right is equal to +4. And same thing on the other side. The limit as x approaches -1 from the left is equal to -4. So although at jumps we would say that we cannot say that it approaches a single numerical value, we can have a one-sided limit and say that coming from a certain direction, it's going to equal a value if in fact there is a jump, like we do have here. All right, and then for limits at infinity, limits can also be used to describe how the graph behaves as x approaches infinity. So far, up to this point, we've only looked at as x approaches 2, as x approaches -1. But what about as x approaches infinity? Well, as x approaches infinity, we're really talking about the far ends of the graph, or in other words, we're talking about the end behavior of the graph. So to give an accurate answer here, we should just use the techniques that we know for calculating end behavior and not just the graph. Okay, so take a look at our next example here. So we have f of x equals 2x squared minus x minus 28 all over x cubed minus 4x squared minus 3x plus 18. So to determine the limit of this function as x approaches infinity, we want to look at the end behavior. So the end behavior we can determine by comparing the degree of the numerator and the degree of the denominator. So the degree of the numerator is 2, the degree of the denominator is 3, so since the degree of the numerator is smaller than the degree of the denominator, we know that the end behavior is going to approach the horizontal asymptote y equals 0. So, for our limit as x approaches infinity, we would say the limit of this function as x approaches infinity is equal to 0. As you go farther and further along the x-axis, closer and closer to infinity, this graph, the y value is going to look more and more like that horizontal asymptote at 0. So if you look at the graph here, if you look at the right-hand side, you can see that it gets very, very close to, never actually touches, but if it gets very, very close to 0. So describing this function as x gets larger and larger, we would say that the y value is equal to 0. Take a look at the next example. We have x squared minus 2x minus 8 all over x squared minus 7x plus 12. So again, we're going to look at the end behavior. And to determine end behavior, compare the degree of the numerator and the denominator. In this case, they are the same. And when the degrees are the same in the numerator and the denominator, the horizontal asymptote that determines the end behavior is going to be the leading coefficient divided by the other leading coefficient. In this case, 1 over 1. So our horizontal asymptote here is y equals 1. So the limit of the function as x approaches infinity is equal to 1. So in other words, as x gets larger and larger, the y value gets closer and closer to 1. And you can see that in this graph here. All right, the last example. We have x cubed plus x squared minus 8x minus 12 all over x squared minus x minus 2. In this case, the degree of the numerator is larger than the degree of the denominator. This means we're going to have a slant asymptote, and the slant asymptote you would determine by dividing, and whatever that quotient is your slant asymptote. So dividing x cubed plus x squared minus 8x minus 12 divided by x squared minus x minus 2 is going to give you x plus 2, possibly with a remainder, but we don't care about the remainder for the slant asymptote. So y equals x plus 2 is your slant asymptote. So now when we talk about the limit of the function, this is going to be the same as the limit of that slant asymptote. So I'm going to replace this with x plus 2. Now, if you were to plug in infinity into this equation here, you would have infinity plus 2, which is equal to infinity. And if you look at the graph itself, remember this is a slant asymptote. So as x gets larger and larger, what happens to your y value? It still gets larger and larger. Because this is a slant asymptote and not a horizontal asymptote, it's not going to approach a specific value. But with slant asymptotes, it's not always going to be infinity. For example, if the slant asymptote was y equals negative x plus 2, then it would be approaching negative infinity. So those were 3 examples of all 3 cases of the different end behaviors and how you would determine, based on the end behavior, what the limit of the function is as x approaches infinity.